Welcome back. This will be the second half of our video lecture on section 2.2. We're looking at direct methods for solving linear systems. Now, if you remember, in our first installment, we covered the echelon form, elementary row operations, and Gaussian elimination. So in this lecture, we'll pick up where we left off. We'll do Gauss-Jordan elimination, homogeneous systems, and linear systems in ZP, where P is a prime value. So let's begin where we left off with Gauss-Jordan elimination. Now, before we start Gauss-Jordan elimination, let's remind ourselves of what we've been doing and why we've been doing it. Remember, our goal is to solve systems of equations, to describe the solution set to a system of equations. And what we've done so far is we've encoded the system in an augmented matrix. Now, using a sequence of elementary row operations, we have been trading off this system step by step for equivalent systems until we get to a resting place that we've been calling row echelon form. Once we have the system in row echelon form, we can solve it by back substitution. And in this case, we'll have a unique solution. The second equation will specify the value of the variable y, and the first equation, now that we know the value of y, will specify uniquely the variable x. So this is a case where this system has a unique solution, and by equivalence, this system has that same unique solution. Okay, so that's one thing that can happen. Now here's another thing that can happen. Here's a system of three equations and three unknowns. After doing our elementary row operations, we get it into row echelon form. But in this case, we have a row of zeros at the bottom. Now that's not inconsistent, so there's no inconsistency here. This system is still consistent, but it does have a free variable. If I name the variables x, y, and z, we can see that this variable here, the one that corresponds to column 2, y, is in fact a free variable. And in this case, that's going to mean that there are an infinite number of solutions. That free variable, in some sense, gives us a degree of freedom, a parameter that we can slide through the real numbers and produce an infinite number of solutions. So that's a possibility. Here's the third example. We start with a system of equations. Through a sequence of elementary row operations, we continue to trade it off for equivalent systems until we come to this resting place of row echelon form. Now in this case, we do have an inconsistency, and it's present here in this third equation, which says 0x plus 0y plus 0z equals 5. And at this point, we know that this system is inconsistent, and by equivalence, this system is inconsistent. There's no solutions to this system at all. So we know that when we're looking at systems of equations, that we can have unique solutions, infinitely many solutions, or no solutions. And we can see how to recognize when we're in each of these cases through the row echelon form. So up till now, that's what we've been doing, and it's a fairly successful strategy. What we want to do, though, is sharpen this a little bit. We want to go to something called reduced row echelon form. So that's what begins our journey today. We're going to be going to something that's a slightly more sophisticated form, but it has some nice enhancements that go along with it. So that's where we're headed. Let's look at the definition of reduced row echelon form. A matrix is in reduced row echelon form if it satisfies the following properties. So first, it is in row echelon form, so it has to conform to the two rules of row echelon form. Number two, the leading entry in each non-zero row is a 1 called a leading one. And number three, each column containing a leading 1 has zeros everywhere else. We're going to look at some examples of matrices that are in reduced row echelon form, but let me draw your attention at this point to an important distinction between the row echelon form and the reduced row echelon form of a matrix. So this is the non-uniqueness of the row echelon form. So there is no such thing as the row echelon form of a matrix. So we never talk about the row echelon form of a matrix because I can take a matrix, let's say like this one here, this augmented system here. I can do one more row operation on it. I can scale row 2 by a factor of 1/4 and get this matrix. And these are both in row echelon form. So they're the row echelon form of the same matrix. So there is no such thing as the row echelon form of a matrix. They're not unique. On the other hand, the reduced row echelon form of a matrix is unique. So if I hand a matrix to Al and Bob and I ask them to produce a matrix in reduced row echelon form, they will produce the same matrix. Now, they may take different paths to the reduced row echelon form, but they will produce the exact same matrix. And so that is an important distinction between the mere row echelon form of a matrix and the reduced row echelon form of a matrix. Let's work this problem. Which of the following matrices are in reduced row echelon form? And let's work from left to right. Now, the very first thing we have to check is that it's in row echelon form. Now, this matrix doesn't have a row of 0, so we don't have to check that. Now, let's identify the leading entries. We have the 1 here, the 1 here, and the 1 here. And as I move down the rows, the leading entries are marching to the right, so that's good. So this is in row echelon form. Now, let's go on and consider whether it's in reduced row echelon form. So we need to check that every leading entry is a 1, and that is true. Each of these leading entries is a 1. Finally, we need to check that each leading entry is the only non-zero thing in its column, the only non-zero entry in its column. And we can see that this is fine. This leading one is all by itself in this column. In fact, this leading one is all by itself in its column. It's the only non-zero entry. We see a problem here, though, in column 2. This leading one has a 2 sitting in its column. So this matrix is not in reduced row echelon form. It's in row echelon form. It's nearly in reduced row echelon form, but it is not presently in reduced row echelon form. Okay, let's take a look at this case in the middle. There is a row of zeros, but it's sitting at the bottom, so that's good. The leading entries are 1 here and the 1 here. And as I move down the rows, the leading entries are moving to the right. Check. Now we have to see that the leading entries are 1s, and in fact they are. And now we need to check that these leading 1s are the only non-zero things in their columns. And this is true for this leading one, and it's also true for this leading one. So this matrix is in fact in reduced row echelon form. All right, finally, let's look at our last example. There's not a row of zeros, so there's nothing to check. The leading entries are the 1 here and the 2 here. And as I move down from row 1 to row 2, the leading entries are moving to the right. So it's in row echelon form. Now, the first thing to check when you're checking for reduced row echelon form, though, is that each leading entry be a 1. And you can see here that this leading entry is not a 1. And so it stops right here. This is not in reduced row echelon form. Now, let's think about what we could do to fix this. Like, how close are we? If I did one more row operation, I could scale this second row by a factor of 1/2, and that would turn this entry into a 1. It would turn this entry into a 4. But once this becomes a 1, this would now be in reduced row echelon form. So this matrix is not quite there, but it's very close. And this first matrix is not quite there, but it's also very close. So we can see that when we get close, we just have to keep doing some additional row operations, and we can get from row echelon form into reduced row echelon form. Now remember, earlier in this section, we were taking a system of equations, putting it into an augmented matrix, using row operations to get it into row echelon form, and then using back substitution to describe the solution to that system of equations whenever that system was consistent. Now, we're going to do something, an enhanced process called the Gauss-Jordan elimination process. So this is a process whereby we can solve a system of equations. So step 1 is to write the augmented matrix of the system of linear equations. Step 2 is to use elementary row operations to reduce the augmented matrix to reduced row echelon form. So this is the enhancement. Instead of going to merely row echelon form, we're going to go all the way to reduced row echelon form. And then in step 3, if the resulting system is consistent, we're going to solve for the leading variables in terms of any remaining free variables. Now that's not that different from what we did before. It's just a little easier to interpret the final result when we've got it in reduced row echelon form. So we'll see that the end game is actually a little simpler if we do the extra step of going to reduced row echelon form. So that's the real benefit. That's one of the real benefits that we're going to get. Let's practice Gauss-Jordan elimination. So in this problem, use Gauss-Jordan elimination to describe the intersection of the two planes. So let's go to the document camera and work out the details to the solution to this problem. All right, welcome to the document camera. Remember, in this problem, we're going to use Gauss-Jordan elimination to describe the intersection of two planes. Now, that's a system of equations, 2 equations and 3 unknowns. And I took the liberty of transcribing that and putting it into an augmented matrix. So our goal is to first use Gauss-Jordan elimination to work this down to its so-called reduced row echelon form, and then we're going to interpret the solution set. Okay, so let's go ahead and do that process of Gauss-Jordan elimination. And I think the first thing we want to do is scan down row 1. The first thing we hit is this 3. And we know that we ultimately want that leading entry to be a 1. So the first step is going to be to scale row 1 by a factor of 1/3 and get a leading 1 in that entry. So I'm going to do 1/3 of row 1. Now row 2 is not changing, so let me just write that one in. Row 1 is being changed by scaling by a factor of 1/3, so that'll become a 1, a 2, a -8, and a 16. All right, good. So I've got my leading 1. My next move is going to use that this newly minted leading 1. I'm going to use it and eliminate anything in its column. Okay? Remember, that's one of the requirements of this reduced row echelon form, is that a leading 1 has to be the only non-zero thing in its column. So typically, once I create a leading 1, my next move is going to be to do some type 3 operations to get rid of anything in its column. In this case, there's just one other row, so it's pretty straightforward. I'm just going to take -2 times that row 1 and tack that onto row 2. All right, let's see what the effect is going to be. Remember, row 1 is unchanged in this, right? So I'm going to keep that row. But now I'm multiplying by -2 and adding down, so that's going to become a 0. When I multiply by -2, that's -4. I add it onto the 7, that becomes 3. We have to be careful here. I'm multiplying by -2, so that becomes positive 16. So 16 plus a -25 is going to be a -9. Now, when I multiply by -2, I'm going to get a -32. When I add that onto the 50, -32 plus 50 is 18. All right, good. So far, so good. I've got a leading entry of 1, and it's by itself in its column. Fantastic. Now I want to move down to row 2. I meet up with this 3. That's going to be the leading entry in row 2. I'm going to turn that into a 1 by scaling. So I'm going to do a type 2 operation here. I'm going to take 1/3 of row 2. So this one's not changing. I'm scaling by 1/3. So I'm going to get 0, 1, -3, and 6. Okay? Now that I've created this new leading 1, I'm going to make sure that I eliminate everything that it's in its column. I want it to be sitting by itself. It's the only non-zero entry in its column. So I'm going to use this 1 to eliminate that 2. And that's going to be done in a single type 3 operation. So I'm going to take a -2 times row 2 and add that onto row 1. All right, let's see what we get when we do that. Now row 2 is fixed. And now I'm going to tack row 1. I'm multiplying by -2 and adding up, so that's going to stay as a 1. I'm multiplying by -2 and adding up. So this was the whole point of using the -2 here. I want to turn that into a 0, so that becomes a 0. I'm multiplying by -2, so that's going to become positive 6. 6 plus a -8 is a -2, so there's a -2 in this position. And then I multiply by -2, so that's -12. I add that on to the 16, so 16 minus 12 is 4. And now I claim we're in the reduced row echelon form. And let's just check. Now there's not a row of 0, so there's nothing to check there. Okay, I've got my leading entries, okay, and they're both equal to 1. As I work my way down the rows, the leading entries are moving to the right, so I've got that. And every leading one now is by itself in its column, right? It's the only non-zero thing in its column. So we're in the so-called reduced row echelon form. So this phase of the problem is over. Now we go into the interpretation phase of the problem. And here it helps to remember that the variable names are x, y, and z. And typically what I want to do now is I want to classify my variables. I want to put them into the two different categories, right? A variable is either going to be leading or bound, or it's going to be free. And that tells us, that tells us a lot about the nature of our solution set. Now, in this case, we can see that x and y are going to be called leading or bound variables because they're governed by these columns which contain the leading ones. Z is free. Let me just label it F. All right. Now the goal is to use back substitution and describe the leading or bound variables in terms of the free variables. So when I think about interpreting each of these rows as an equation, I want to remember that I'm always trying to express leading variables in terms of free variables. So here we go. In this, we're going to work from bottom up. Here we get an equation that says y minus 3z equals 6. And remember, I want to describe the leading one in terms of the free one. So I'm going to write this as y equals 6 plus 3z. All right. How about x? X minus 2z equals 4. That's the same as x equals 4 plus 2z. Now you'll notice there is nothing that constrains z. That's the free nature of z. Z has got the freedom to be whatever it wants to be. And the bound nature of x and y is this, right? Once I specify a value for z, that does fix a value for x, and it does fix a value for y. So we've got this degree of freedom here. I can let z be anything I want, but once I set a value for z, it does fix x and y. So what I want to do is write it this way. I'm going to stack my variables. I'm going to write x, y, and z. And typically, since z is the free variable, we're just going to set it equal to some parameter. Z can be whatever we want, so we'll call that value s. And now I'm going to write y and x in terms of that parameter. So y is going to be 6 plus 3s, and x is going to be 4 plus 2s. And that's a way to express the solution set to the system of equations. I've got this degree of freedom in s. I can set s to be anything, and then x and y will be given values according to these formulas. Now, I think a better way to write this is the vector form of this solution. So let me write it this way. If I think of this as a column vector, I can see that this is going to be the sum of two column vectors. There's going to be the one column, which is the column of these constants. So it's a 4, a 6, and a 0. And then there's the other column that's carrying the s parameter. So 2s, 3s, and s. And then I get a nice geometric interpretation if I pull that scalar s out. Okay, now when I write it this way, I get this nice representation of my solution set. I know that there are infinitely many solutions, but I know more than that. I know that all of my solutions to the original system of equations. Now remember, that system came from looking at two planes in three-dimensional space, right? These are the equations of two planes in three-dimensional space. And what this is telling me is that my solution set conforms to a line in three-dimensional space with a position vector 4, 6, 0. So that's a point that's pointing to a point on that line, and direction vector 2, 3, 1. So I can imagine my two planes intersecting and their points of intersection forming a line. And this is a description of that line in this vector form. So let's just kind of review what we did. We took our system, our two planes, put them into the augmented matrix. We did Gauss-Jordan elimination. We got it down to the row reduced echelon form. We identified the leading or bound variables, the free variables. We wrote the bound variables in terms of the free variables. We set the free variable equal to a parameter. In this case, there was just one parameter, one free variable. And then we were able to express our solution in this vector form and see that it's the equation of a line in three-dimensional space. So we can reinterpret that in terms of the two planes that generated these equations. Okay, let's head back to the class notes and continue our discussion. Let's practice interpreting the reduced row echelon form. So let's take a look at this matrix on the left. It's in reduced row echelon form, and we can see that every one of the variables, let's name them x, y, and z as we move from left to right, each of those is a bound or a leading variable. In this case, we can actually read the solution out immediately, right? We can see that x is equal to 3, y is equal to -1, and z is equal to 7. So when there's a unique solution, it's just very easy to read right out of the reduced row echelon form. Now let's take a look at matrix 2. Now there is a row of zeros, but this doesn't point to an inconsistency because 0 equals 0. Instead, what we have here is we have the presence of a free variable. The variable y does not have a leading 1 associated with it. So we have a free variable in a consistent system, and that is going to point to infinitely many solutions. And we could describe them by simply working out the relationships between z and y and x and y. So we could easily parameterize and describe the solution set to this system of equations. Finally, we have a case like this where we go to the reduced row echelon form and we see something inconsistent, right? We would have 0x plus 0y plus 0z equaling 1, and that's a contradiction. And so we can immediately stop this process and say that the corresponding system of equations has no solution. This is an inconsistent system of equations. So the point of this exercise is to understand that we can interpret the nature of our solution set right out of the reduced row echelon form. Our next topic is homogeneous systems. Now, the definition of a homogeneous system is rather underwhelming. A system of linear equations is called homogeneous if the constant term in each equation is 0. So let's take a look at a couple of systems of equations written in augmented form. We can see that this system is not homogeneous because these constant terms are not all 0. Whereas this system is homogeneous because the constant terms, the terms on the right, are all equal to 0. So this is a rather underwhelming definition. Although this definition is a bit underwhelming, it is important nonetheless because the homogeneous systems of equations play a central role in the general theory of solutions to systems of linear equations. So more on that as the course progresses. Now here's a couple of important things to understand about homogeneous systems. First, observe that a homogeneous system of equations is always consistent. Now, we'll look at this under the document camera, but while we're looking at our next theorem, think about why is that true? Why is it that a homogeneous system of equations is always consistent? Now, let's look at theorem 2.3. So suppose we have a homogeneous system that we put together. We've got a matrix of coefficients paired up with a column of zeros. So this is a homogeneous system. So if this is a homogeneous system of m linear equations with n variables, where m is less than n, then the system has infinitely many solutions. Now, if you're trying to wrap your head about what's going on here, what they're telling us is that the number of equations is less than the number of total variables. So you might imagine a homogeneous system where we have 2 equations in 3 unknowns, or 4 equations in 6 unknown variables. So what they're saying is that anytime we have a homogeneous system of linear equations where the number of equations is less than the total number of variables, we know that we have infinitely many solutions. Now, let's head over to the document camera and we'll talk about the observation and we'll look at the proof of Theorem 2.3. Welcome to the document camera. Let's address a couple of issues that are listed on this page. First, let's talk about this observation, a very important observation. It says, a homogeneous system of equations is always consistent. And the question is, why? Why is that the case? Well, I've got 5 different homogeneous systems of equations here, and what this observation is saying is that each and every one of them is a consistent system. And I wrote these down somewhat arbitrarily, but I am guaranteed that these systems are consistent. And the question is, why must that be the case? Well, let's remember what it means to be consistent. A system is consistent if it has a solution at all, whether that solution is unique or whether there are infinitely many solutions. A system is consistent if it has a solution at all. And so the question is, in each one of these cases, can you guess a solution to the system of equations? So think about that. Can you guess a solution to each and every one of these systems? Well, in this first equation, I can set x and y both equal to 0, and I get a solution. In my second equation, I can set x, y, and z simultaneously equal to 0, and I get a solution. And you can see the pattern here. In each and every case, by setting each of the variables equal to 0, we're guaranteed a solution to the system of equations. So a homogeneous system, by virtue of having all of these constants equal to 0 on these right-hand sides, we're guaranteed that there will be a solution, a trivial solution, just by setting all of the variables in question equal to 0. So a homogeneous system of equations is always consistent. Now let's take a look at Theorem 2.3. If a homogeneous system of m linear equations with n variables, where m is less than n, then the system has infinitely many solutions. So if m is less than n, then the system has infinitely many solutions. Now, let's see what this condition means. This says that the number of equations is less than the number of variables. Now, in the homogeneous systems that I've listed here, the first 3 meet that condition. I've got 1 equation, 1 row, and 2 variables. I've got 2 equations and 3 variables. Here I've got 4 variables and 2 equations. So each one of these systems meets the condition of Theorem 2.3. And this is typically what's called understated, right? We have more variables than we have equations to bind them. So 1, 2, and 3 are typically called understated. Okay, so that's the term that we'll use. 4, in system 4 here, I've got 2 variables and 3 equations, and 4 is what we might call overstated. And by overstated, we just mean that there are more equations than there are variables in question. So I've got three equations and 2 variables, and that's what's called overstated. And 5 is kind of the nicest situation. I've got as many equations as I have variables. We might call that perfectly stated. I have as many equations as I have variables. Now, the important thing to understand here is in Theorem 2.3, we're only addressing the understated case. So this is the only case that's being addressed in Theorem 2.3. And I think it helps to understand what this means in terms of the matrix A. So M is the number of equations, and so we can think of M as equivalent to the number of rows. I'll just notate that by saying m is equal to the rows of A. It's the number of rows of A. And n is the number of equations, and that's equivalent to the number of columns. So the number of rows and the number of columns. And what we're being told is that there are more columns than rows. All right, so if we think about the shape of that matrix, it's going to be rectangular and it's going to be elongated. It'll be wider than it is tall, so to speak. Okay, now let's think about what's going on here. All right, let's go back to the concept of rank. Let's see what we can say. We know that the rank of the matrix A is going to be the number of non-zero rows in its row-reduced echelon form, or even in its row echelon form. So it's the number of non-zero rows. Now we know if we only have m rows to start with, that the rank has to be less than or equal to the number of rows, period. Okay, now let's multiply both sides by -1. That's going to flip the inequality. So the negative of the rank is going to be bigger than or equal to the negative of the number of rows of A. Now I did this for a reason. I want to add the number of columns of A to both sides of this inequality. So I've simply taken this inequality from above and I've added the same thing to both sides. So I preserve the inequality. And now I just have to interpret what I'm staring at here, right? The number of columns is equal to the number of equations. And so this is n minus the rank of A. And over here I've got what? The number of columns, that's n, and the number of rows, that's m. So this is going to be n minus m. Okay, now what are we being told? We're being told that n is strictly bigger than n. N is strictly bigger than m. So n minus m, whatever this is, it's a positive number. And so that says n minus the rank of A is strictly positive. Okay, now what does the rank theorem tell us? We studied the rank theorem. The rank theorem tells us that n, the number of variables, minus the rank is the number of free variables. And so this is telling me that the number of free variables is strictly positive. That means that there has to be at least one free variable, maybe more. But the point is, once we have the existence of a free variable, just the existence of one free variable already tells us that we have a degree of freedom, a parameter that we can run through the entire set of real numbers that's going to give us infinitely many solutions. There might be more than one free variable, but we're guaranteed the existence of at least one free variable, and therefore we have infinitely many solutions. Not just a solution, but infinitely many solutions. All right, I want to make one last comment on Theorem 2.3. Remember that Theorem 2.3 is just telling us something about the case when m is less than n. So it's telling us that in the cases of these understated systems like 1, 2, and 3, we're guaranteed, just looking at them, that we have infinitely many solutions. The theorem is not telling us anything about this case 4 where we have the overstated system, and it's not telling me anything about this case 5 where we have the perfectly stated system. All we know by this theorem is that when we have an understated system, we're guaranteed infinitely many solutions. There might be infinitely many solutions to this one, and there might be infinitely many solutions to this one, but we don't know from Theorem 2.3. It doesn't address the situation where we have overstated or perfectly stated systems. So just understand the importance of Theorem 2.3. It tells us something very useful in the case of these understated systems, but it's not addressing the overstated or the perfectly stated case at all. All right, let's head back to the class notes. Let's close this subsection on homogeneous systems by solving a homogeneous system of equations. So let's head over to the document camera and work out the solution set for this homogeneous system of equations. Welcome to the document camera. I've taken the liberty of taking that system of equations and putting it into an augmented matrix. And the homogeneous nature of the system is reflected here in this column of zeros sitting here on the right. Now, here's what we're going to find, right? As we do elementary row operations on this augmented matrix, we're going to find out that there is never going to be any change to this column of zeros, right? Every one of our every type of elementary row operation is not going to change any of these zeros. And so typically what people do is they just save themselves the time of constantly rewriting this column of zeros. You just concentrate, when you're working with a homogeneous system, you merely concentrate all of your attention on the matrix of coefficients. So what I'm going to do is just start. This is where I would start typically. I wouldn't write that constant column of zeros. So I would typically start right here. I'd say, here's my matrix of coefficients. It's a homogeneous system, so I know that that's hanging off to the side there, but I'm not going to write it every time. All right, so typically we start here. All right, now what I want to do is go through a sequence of row operations to try to get this down into this reduced row echelon form. And so the first thing I'm going to do is turn this leading entry in row 1, I'm going to turn that into a 1 by using 1/2 of row 1 as my operation. So I'm going to scale row 1 by a factor of 1/2. And so this is going to have a change only in row 1. It's going to become 1, -2, and 2. Row 2 is unchanged. And row 3 is unchanged. Now, having created that leading 1, I'm now going to use it to take out the 5 and the 3 that sits in this column. Remember, our goal is to have a leading 1 be the only leading entry in its column. It's the only thing in the only non-zero thing in its column. So I have to remove the 5 and the 3. And so I'm going to do that with a pair of type 3 operations. So I'm going to go. I'm going to take row 1 and scale it by -5. And I'm going to add that onto row 2. Then I'm going to take row 1, scale it by -3, and I'm going to add that onto row 3. So here are my two type 3 operations. Now, what's the effect going to be? Remember, I'm multiplying first by -5 and then adding down, so that's going to become 0. Let me rewrite my row 1 here first. So this is going to become 0 in this position. When I multiply by -5, that becomes 10. And so that becomes 0 in this position. That becomes -10 added onto the 15. So that's going to give me a +5. Okay, and that takes care of row 2. Now let's go to row 3. I'm multiplying by -3 and adding down onto row 3. So that's a 0. That becomes a +6 added onto the -6. So that's also a 0. That's interesting. And then I've got -6 added onto the 9. That's going to give me a 3. Okay, now I scan down row 2. I want to turn this into a 1, so I'm going to scale row 2 by a factor of 1/5. And so this simply changes this row into 0, 0, 1. This row is unchanged, and this row is unchanged. And now I've got one more step. Well, two operations, but I can do them kind of simultaneously here. I'm going to use this new leading 1 that I've created, and I'm going to go up and down and eliminate those things that sit in its column. And that should bring me to the row reduced echelon form. Let's find out. So I'm going to have to take a -2 times row 2, and I'm going to add that onto row 1. And a -3 times row 2 added onto row 3. Now row 2 is unchanged, so I'm going to rewrite that one right away. And let's see the effect. Now this row has lots of zeros in it, so this is pretty simple. I'm multiplying by -2 and adding up, so that's going to have no change there. No change in this position. And here's the change that we wanted, right? When I multiply by -2 and add up, that becomes a 0. And I'm multiplying now by -3 and adding down, so no change, 0. And now I claim we're finally in the row-reduced echelon form. Now, let's just check to make sure, right? Are we in row-reduced echelon form? Well, we have a row of zeros, but it's appearing at the bottom, so that's rule 1. Okay, our leading entries, the 1 and the 1, conform to the rule that as I move down through the rows, the leading entries are moving to the right, so we've got that. And finally, we want to make sure that every leading entry is a 1, which it is, and it's the only non-zero thing in its column. So we've achieved the reduced row echelon form, so we're good to go there. Now what we have to do is interpret our solution, right? The whole goal of going through this exercise was to describe a solution set that corresponds to this original homogeneous system. Now, at this point, it helps, you don't have to write this, but it helps to remember that all along we've essentially been dragging along this column of zeros. So in a sense, remember that there's a column of zeros that was attached to the original augmented matrix, and we can reintroduce it here just for interpreting this result. Now, before we do that though, let's remember that our variables were called x, y, and z. And let's remember that since x is corresponding to a column containing a leading 1, that's going to be what's called a leading or a bound variable. So let's just label it L for leading or bound. Z is also a leading contains a leading variable, so it's going to be called a leading variable. But y does not have a leading variable, or excuse me, a leading entry in its column, so it's called a free variable. Okay, so we've got 2 bound or leading variables and 1 free variable. All right, that's important because the existence of that free variable tells me that there are infinitely many solutions to this system, right? And we'll explore that in just a second. But we've got our variables x, y, and z now typed between the type that are leading and the type that are free. Now, let's go through the process of back substitution to explore the solution, right? So we're going to start from the bottom and work our way up. Our last, of the equations that carry any content at all, this second equation is telling us that z is equal to 0. Okay? The only other equation we have is equation 1, and when we work that out, it's telling me that x minus 2y is equal to 0. Now, x is a leading or a bound variable, so I'm going to express it in terms of the free variables. And so in this case, I'm going to write x equals 2y. And we know that y is free. And typically what we do is we set y equal to some parameter that we can just vary throughout the whole real number. So we'll just say y is equal to some parameter s, where s, we can think of s as ranging through the entire set of real numbers. So every time I specify a value for s, it fixes the value for x, right? So x is bound. It's bound by the value that we set for y. So once I set a value for y, I give it some value s. That sets x equal to twice s. And z, no matter what, is always equal to 0. So that's the bound nature of the variable z. So we see that x is bound by y, z is equal to 0, and y is just free to be whatever it wants. So one way to write out the solution is just to list the variables in order and just say x is equal to twice s, y is equal to s, and z is equal to 0. That's one way to do it. But in vector form, it would look like this. We would say the vector x, y, z is equal to 2s, s, 0, which is better expressed by pulling the scalar out I'm going to put this in here. It's not doing anything. It just helps to visualize what the solution is saying. Okay, it's telling me that any solution to the original system of equations, so think of this vector as a solution to that original system. What is it? It's on a line passing through the origin, there's the 0 vector, plus it has direction vector 2, 1, 0. So all the solutions lie on a line passing through the origin with this direction vector. So that's a geometric interpretation of the solution to the original system of equations. So notice that you get that trivial solution. That's going to be part of every homogeneous system. You always get that trivial solution, and this is saying you get also all of the vectors that lie on this line with this direction vector. Okay, so let's head back to the class notes to discuss some more material. Our last topic for section 2.2 is linear systems in Z sub p, and we're going to focus on the case where p is a prime number. Now let's use as our exemplar, let's look at Z5. So what I've got here on the screen is the addition table for Z5, and I've got the multiplication table for Z5. And in both of these tables, I have some entries that are in red, and I want to look at each of these as special entries in the table. So the first thing is, let's look at the addition table. For every number, 0, 1, 2, 3, or 4, there's an entry in the addition table that's red, and what that's highlighting is that, for example, 1 plus 4 is equal to 0. So 1 and 4 are what are called additive inverses. If I add 4 to 1 or 1 to 4, I get 0. 2 and 3 are additive inverses. If I add 2 to 3 or 3 to 2, I get 0. So the important thing is, by looking at this addition table, I can see that every element of ZP has what's called an additive inverse. Now, that's actually true just in general. P doesn't have to be a prime number for that property to be true, but it is one thing that I want us to notice with Z5 is that every element of Z5 has what's called an additive inverse. And it's actually very easy to think about how to construct the additive inverse. If I hand you a number like 2, you just have to think, what would I have to add to 2 to get to 5? All right? Now that works for every number except 0, but in general, if I'm sitting at 3, I think, what do I have to add to 3 to get up to 5? And that's the number 2. And so 3 plus 2 is equal to 0 in Z5. Okay, so we have additive inverse. Now, this is what's special to prime numbers. So when we're looking at ZP, where p is a prime, we're going to see this additional feature. Here's the multiplication table for Z5. And what I want you to notice is that in every row except the row 0 and the column 0, I've got a red 1. And that is pointing to what's called a multiplicative inverse. So for example, in this multiplication table, I can see that 2 times 3 is equal to 1. In other words, 2 and 3 are multiplicative inverses of each other. So if I take 2 and multiply it by 3, I get 1. And if I take 3 and multiply it by 2, I get 1. So in some sense, 2 is acting like 1/3, and 3 is acting like 1/2. Okay? So every number other than 0 has what's called a multiplicative inverse, and we can see it in this table by the ones that are appearing in each and every non-zero row and non-zero column. All right, so I've got the multiplicative inverses down here. 1 times 1 is 1, 2 times 3 is 1, 3 times 2 is 1, and 4 times 4 is 1. So from this table, we can always find the multiplicative inverse of any non-zero element of ZP. Now, this is important because what we're going to do is we're going to be looking at systems of equations where the elements, instead of coming from the real number system, they're going to come from Z5. We're going to work an example in Z5. But in general, we could work an example just like it in any Z sub p, where p is a prime number. All right, so we're going to work in Z5 in particular. But we're going to be looking at a system of equations in Z5, and we're going to want to find solutions to that system of equations. So let's take a look at our example. All right, so here's a system of equations in Z5. We're going to use Gauss-Jordan elimination to solve this system. So our first equation is 1x plus 2y plus 2z equals 0. 4x plus 2y plus 1z equals 1. And our third equation is 2x plus 2y plus 0z equals 2. Now, what are we looking for? What is a solution to this equation? It's a value of x, y, and z, all coming from z5, that simultaneously satisfy each of these equations. Now, what we're going to see is we can use all of our standard techniques. We can use Gauss-Jordan elimination. The only thing we have to remember is that we have to think in terms of additive inverses in Z5 and multiplicative inverses in Z5. So let's head over to the document camera and watch the solution to this problem, paying special attention to the fact that we're in Z5 instead of the real numbers, and so we have to make some adjustments accordingly. So let's head over to the document camera. We'll look at this problem and see its solution. Welcome back to the document camera. I've taken the liberty of taking the system of equations in Z5 and writing it as an augmented matrix. Now, our goal here is to just row reduce this. We want to get this into reduced row echelon form using elementary row operations. The only thing we have to be attentive to is that all of our work is in Z5. So we're going to have to rethink, rehabituate ourselves to the idea of working in Z5 rather than working in the real numbers. And I think we'll adapt pretty quickly once we get the handle on this. So let's begin like we always would begin. We're going to look in this first row and we're going to see we already have a 1 there. We already have a leading entry that's a 1, so we feel good about that. Now we're going to use some type 3 operations to eliminate the 4 and the 2. Now, we have to take some care here. Now, I'm trying to eliminate the 4, and if we were working in the real numbers, we would be using negative 4 times row 1 and adding it on to row 2, the idea being that negative 4 is the additive inverse of 4 in the real number system. Now, in Z5, we have to think of what is it that I would add to 4 to get me to 0. And we have to get to 5, so I would add 1. And by adding 1 to 4, I get to 5, which is 0 in Z5. So I need to multiply row 1, not by negative 4, but by 1, because we're working in Z5. And I'm going to add that on to row 2. Now we have to do the same thing here. We have to imagine in Z5, what would I add to 2 to get to 0? And that would be the number 3, because 2 plus 3 is 5, and 5 is equivalent to 0. So I'm going to do 3 times row 1 and add that onto row 3. Now, row 1 is not changing in this. So that one goes through as 1, 2, 2, 0. Now, all of our multiplication and addition has to be done in the Z5 sense, so let's be careful. Now we're in luck here, we're just multiplying by 1, so this is still going to be 1. 1 plus 4 is 5, which equates to 0, or is equivalent to 0. All right, so 1 times 2 is 2, 2 plus 2 is 4, and that already makes sense in Z4. And then 1 times 2 is 2, plus 1 is 3. 1 times 0 is 0, and that just becomes 1. So there's our first type 3 operation. Now we're going to do this. We're going to multiply by 3 and add on to row 3. Now here we have to be a little careful, right? 3 times 1 is 3, and 3 plus 2 is 5, which is 0. That was the whole point of using the 3. Now, 3 times 2 is 6, but 6 is equivalent to 1, and 1 plus 2 is 3. Okay, 3 times 2 is 6, which is 1 in Z5. Remember, we're always interpreting everything in the Z5 sense, so 3 times 2 is 6, or 1 in the Z5 sense, and 1 plus 0 is 1. And then 3 times 0 is 0, plus 2 is 2. Okay, so we've got our leading entry as a 1, and it's in this column. It's the only non-zero entry in its column. Now we go down to row 2, and we need to turn this into a leading 1. Now, normally, if we were working in the real numbers, we would be multiplying by something that would turn this into a 1. That's why we would scale. Typically, we would scale by 1/4. Now, in the Z5 sense, we have to think of what would I multiply 4 by in Z5 to get a 1? And if you remember, 4 times 4, which is in normal integer arithmetic, 16, that is 1 in the Z5 sense. So I'm going to multiply or scale row 2 by 4. So if you're trying to remember what's going on here, we're just using the fact that in Z5, 4 times 4 is equal to 1. So we're trying to affect that change here. So we're multiplying row 2 by 4. Let's see the effect of that now. This row is not changing. Row 3 is the same. Row 1 is the same. So let's get those in place. Now let's go along row 4. 4 times 0 is 0. 4 times 4 is 16 or 1. That was the whole point of this scaling. Let's be careful with this one. 4 times 3 is 12, which is 2 in the Z5 sense. And then 4 times 1 is 4. Okay, so that's the result of that type 3 operation. Now, every time we create a leading 1, our next move should be some type 3 operations to go off and eliminate those elements that are in its column. So we have to get rid of the 2 here in row 1 and the 3 there in row 3. All right, so we have to think about how we're going to do that. Okay, so I have to think, what am I going to multiply this 1 by to give me a number that when added to 2 goes to 0? And that number must be 3, because 3 plus 2 in the Z5 sense is equal to 0. So I'm scaling row 2 by 3 and adding that on to row 1. That's going to eliminate that 2. So we have to think in terms of additive inverses. Okay, likewise, what do I need to add to 3 to get to 0 in the Z5 sense? That's 2. So I need to do 2 times row 2 added onto row 3. All right, let's take a look at the change that's going to occur in row 1. So I'm multiplying by 3 and then adding up. So 3 times 0 is 0, added onto 1 is still a 1. Beautiful. 3 times 1 is 3, added onto the 2 gets me to 5, which is equivalent to 0. Okay, let's be careful here. 3 times 2 is 6, that's 1 in Z5, and 1 plus 2 is 3 in Z5. All right. Here's our recipe. We're doing 3 times 4, that's 12, that's 2 in Z5, and 2 plus 0 is 2. All right. Now let's work out the new row 3. Our recipe is 2 times added down. So 2 times 0 is 0, plus 0 is 0. 2 times 1 is 2, added onto the 3, that's 5 or 0 in Z5. Again, that was the whole point of using the 2. 2 times 2 is 4. 4 plus 1 is 5 or 0. And here we go. Our last operation here is going to be 2 times 4 is 8, which is 3. 3 plus 2 is 5, which is 0. And I think we're done. Let's check. I'm claiming that we are now in reduced row echelon form. Now this augmented matrix does have a row of zeros, but it's at the bottom, so we're good. We've got our leading entries. They're 1s. As I move down the rows, the leading entries are moving to the right. And each leading entry, which is already a 1, is by itself in its column. It's the only non-zero element in its column. So we've achieved the row reduced echelon form. Now let's characterize the variables that we've got here. Right? Our variables are x, y, and z. X is in a column with the leading 1, y is in a column with the leading 1, and z is not. So these will be a leading variable, and a free variable. So z is free. X and y are bound. They're going to be tied to the free variable or specified directly. Now, we have to be careful, and this is why I think it's fun to work this problem. First of all, it's fun to work this problem in Z5 just because it forces us to rethink what we're doing when we're doing these row operations and how we would create these different scalings and type 3 operations. But what's more fun is to think about what this means. Normally, we would think of this as the presence of this free variable as the existence of infinitely many solutions. And in fact, that's not going to be the case. Let's see why. All right, so z, we're just going to equate with some parameter s. And now we're going to try to describe x and y in terms of z. We're going to try to fill this out using this parameter s. Now, let's look at this bottom equation. That says that y plus 2z equals 4. Now, I want to bring this to the other side. I want to write y in terms of z. Now, normally we would think of subtracting 2z from both sides, but I have to think of adding something that will turn this into a 0, and that's going to be adding 3z to both sides. Okay? 2z plus 3z is going to be 5z or 0z. So that is going to be 0. So y, in fact, is equal to 4 plus 3z. Okay, so let's write that in. If z is equal to s, 4 plus 3s. Okay, now let's do the same with this top equation. X plus 3z equals 2. Okay, now if you're on the right wavelength, if you've gotten something out of this first one we did, you'll know that what we need to do is add something to both sides that will bring this to 0, and that's going to be 2z. So by adding 2z to both sides, this will become 5z or 0, and this will be plus 2z on this side. So x equals 2 plus 2z. And so in terms of the parameter s, we would write that as 2 plus 2s. Okay? In vector form, we would write this as we'll have the constant vector 2, 4, 0. We'll have a parameter multiplying the direction vector 2, 3, 1. Now I'm borrowing the language from working in three-dimensional space. I'm thinking of this as a line that goes through a point with a certain direction. But we have to remember that we're in Z5. So here's the difference. Here's why, even though that we have this presence of this free variable, the reason we don't have infinitely many solutions is because, remember, S itself, this parameter, has to come from Z5. And so there are only 5 choices for S. There aren't infinitely many choices for S. There are 5 choices for S. S equals 0, 1, 2, 3, 4, and 5. I don't know if I said that correctly. Let me try it again. There are 5 choices for S, 0, 1, 2, 3, and 4. Those are the 4 elements of Z5. Now, I won't work all of these out. I just want to show you what happens as we march this parameter through these different values of S. So when S is equal to 0, we're going to be pulling out the solution 2, 4, 0. When S is equal to 1, we're going to have 2 plus 2, or 4. 4 plus 3, which is 7, which is equivalent to 2. And 0 plus 1, which is equivalent to 1. Okay, now you can keep going. You can plug in S equals 2, S equals 3, and S equals 4. Now remember, we're doing multiplication here, so you'll have to attend to the multiplication. Let's work out this last one, just so you can kind of see. So I'll leave these 2 for you to try. Let's do the S equals 4 case. Well, let's be careful. When S equals 4, this is going to be 4 times 2. Now normally that's 8, but in Z5 that's 3. And then 3 plus 2 is 0, so our first component is 0. Now we'll have 4 times 3, that's 12, but that's 2 in Z5, and 2 plus 4 is 6, which is 1 in Z5. Finally, when S is equal to 4, that'll be 4 times 1 or 4, and 4 plus 0 is 4. Okay, so I'll leave you to work out these middle 2. But the point is, I think we've reached the point. The point is that we have a free variable here, but since we're in Z5, rather than having infinitely many solutions, we just have as many solutions as there are values for that parameter, right? So Z can take on a value from 0 through 4. So we're going to get 5 different solutions to that system of equations. All right, so hopefully that was exciting. It shows you that this row-reduced echelon form is achievable even when we're working in Z5 as opposed to the real numbers. And so we can kind of modify the way we think about our constructing our are different types of row operations, reflecting the fact that we're in Z5 rather than the real numbers. And so it's a good mental exercise. It's a good way of thinking about how to solve problems like this. All right, so that's all I wanted to show you, and that brings a conclusion to this second half of Section 2.2. So I hope you enjoyed that. I'll see you again for some video lectures on Section 2.3.